Okay, if you haven't already started to wonder, at least I'm curious. We've been given all this information about molecular structures, and um, we know from general chemistry that we can determine the empirical formula and the molecular formula simply with uh, mass percent and true molar mass. That's easy to do. But now with organic chemistry, the structure, actually how the molecules put together, is critical to understanding how the molecules react. So I remember when I was being tortured by my organic chemistry instructors, the way that it was just starting the methodologies with mass spectrometry, and then the other light-based spectrometries, infrared, visible, and ultraviolet. That the only way to confirm or to prove, if you wanted to publish a work, you have created a new molecule and you wanted to publish a work, or you had a product from a reaction and you wanted to prove what the molecule was and what its structure was, then in order to do that, you had to synthesize a molecule by known techniques, known reactions that would give you only certain products, intermediates, as you proceeded through the rebuilding of the molecule. Then you could prove that the outcome that you were proposing in your publication was the true one. It's a lot simpler now because we have these techniques, and we're going to start with mass spectrometry as helping us determine the structure of a molecule. And we call it a spectrum simply because it breaks the molecule apart into different pieces. We sort of borrow the terminology from light-based spectrometries, where visible is like red, orange, yellow, green, blue, indigo, violet, or the ones that we can't see, ultraviolet, infrared. We break those into various wavelengths, and that's our spectrum. But for mass spectrometry, our spectrum is based upon the mass to charge ratio of various fragments that we can produce from a given molecule. We're going to get into infrared spectrometry in chapter 16, and actually ultraviolet and infrared. And then 17, we're going to look at nuclear magnetic resonance, which is actually the spectrometry of the nucleus itself. And all these techniques can go together to confirm the structure that you're proposing for a given molecule. So it's kind of like a detective story. You're piecing things together, and after, what was it, Sherlock Holmes used to say, if you eliminate all the improbable ones, what's left, no matter how impossible, must be the right one. I paraphrase. Okay, so mass spectrometry is based upon the response of a moving charge or a charged ion through a magnetic field. So this is a representation. This is the way mass spectrometers used to use. They were called magnetic sector mass spectrometers. And you would take a sample, preferably a very small sample, and you inject it into the device, and there's a heater that vaporizes it. The sample must be in the vapor phase to start with. Then you have an accelerator plate, and this sample goes through the middle of the accelerator plate, and it's not accelerated yet because it's not an ion. Right? You're injecting a neutral compound into this device. But once it gets between the two accelerator plates, we hit it with an electron beam. And that electron beam is adjusted just so that you can produce a single positively charged ion. Now, this would be true for the entire molecule. You would knock one electron off, that would give you a positive charge. It has to be charged because you can't accelerate a neutral compound through an electric field. So once it's charged, then those two plates will allow you to accelerate your charged ion up to a given velocity, and then it goes into the magnetic sector. And the magnetic fields are this way, and they respond perpendicular to that field. So they're going to bend in that field. Now, the ones, they're all going to have, we've adjusted everything so that the ions produced are only a single positive charge. So that means we've knocked one electron off of them. That means we really haven't changed the mass at all, because one electron is 1,800 times smaller than a proton anyway. So one electron missing is not going to be missed. But we produce this positive charged ion and introduce it into the magnetic field, and it bends, right? How much does it bend? Well, the force is going to be the same. It's based upon the charge. The magnetic field strength is constant, and the charge is the same for every ion going through that field. The difference is the mass. So the force is applied to that mass, and the ones that are going to bend the most are the lightest ones. So they'll bend furthest to the right, and the ones that are more massive will bend to the left. Okay, most instruments, though, don't have enough room to spread everything out like that and have all these detectors there. So we have one detector, and what we do is we vary the magnetic strength. We scan it through a various strengths of magnetic field so that we can pick up all the peaks on a single detector. Now, the only reason we can do this is because the detector electronics now are so fast that they can pick up individual strikes on the detector, and they count them. So as the field is this strength, it counts how many strikes are at that strength, and we step it through the various strengths. And you build up a profile, a spectral profile that's there on the right. M divided by Z is mass divided by charge. Right? So since the charge is +1, we just say all the peaks, all the peaks are proportional to the mass. Now, I've been speaking as if we just charged the single molecule. That would give us just one peak, wouldn't it? But as a matter of fact, when we hit that molecule with an electron beam, we're going to break bonds. So we're producing fragments as well. And that's what all those other peaks are. The very largest peak to the right, the furthest right, except for the little tiny one that you can see down below the farthest one to the right. We'll talk about that one in a minute. But the biggest one to the right is the intact molecule that's charged. And everything to the left are fragments. Okay. Now, there are some labs that still use the magnetic sector because for many applications, it's much more accurate. And it's able to separate fragments with higher resolution. But they're very expensive. So things like we've been able to couple various chromatographic techniques like gas chromatography with mass spectrometers. So if you see somebody says, yeah, I operate a GCMS, they're saying I have a gas chromatograph and the detector is a mass spectrometer. I used to operate one, but it did not use a magnetic sector MS. It used another technology called the quadrupole that mimicked the effect of a magnetic field and produced similar results for a lot less money. Okay. So here's what happens in the process. You put a very, very small sample, smaller the better, that you can get away with. In this case, less than 1 microliter. And the first thing that happens is we turn it into a gas. It goes through a heater. We vaporize the gas. Then we hit it with an electron beam and we ionize it. And not only ionize it, but while it's in there, we fragment it. We produce fragments. And these fragments tend to follow a pattern. And we're going to look at that in a subsequent slide. Only the weakest bonds are going to be broken by this impact from these electrons. And the electrons are being driven through the sample vertically, and they're being collected. Let's go back to that picture. They're being collected on the other side, right? So you don't have these electrons flying into your magnetic sector, interfering with your detector. They only impact the sample long enough to do their job, and then any extra ones are drawn off into the collector. Okay. All right. So this has a fancy name. It's called electron impact ionization. Imagine that. There are other ways to ionize your sample. There's a chemical ionization that's possible also, but that's only used in special circumstances. In general, electron impact is the preferred and most commonly used method. Okay, so I mentioned this earlier. The detector can detect the electronics are so fast that the detector can pick up individual strikes of these ions, and then it orders them by relative abundance. So the fragment with the greatest number of impacts is going to be given 100% relative abundance. That's known as the base peak. So you're always going to have one peak that goes all the way to the top of your graph. And then everything else is relative to that. So here's an example of 1, 2, 3, 4, 5, 6 hexane, normal hexane. The base peak has a mass of 57. It has a mass to charge ratio of 57, but since we've adjusted everything so that it's only a single positive charge, we can also say it's 57 atomic mass units. So that's our 100% base peak. That's the most abundant fragment. And then the largest peak to the right is 86. So we take that to be the 86 atomic mass units for hexane. Now, is that right? Let me get my calculator. I don't like to take them at their word. So what's the formula for hexane? We know normal hexane should have 6. Oops. That's not right. 6 carbons. How many hydrogens for an alkane? 6 plus 1 times 2, 14. 14 hydrogens. Or 4 of the carbons have 2 hydrogens, and 2 of the carbons have 3. So that's why it looks like that. Okay, now let's add them up. What's 6 times 12.01? 6 and 12, 7206. And then 14 hydrogens is 14.8. Right? No, wait a minute. That may not be right. 1.01 times 14. 404.1. Yeah, I was right. 1440. Okay, so that's 0, 2, this is 6, 86.2. Okay, so they got it right. 86. So that's the molecular ion peak is 86. We're going to start introducing some rules that help us interpret the graph. We're going to be able to propose formulas, molecular formulas for the molecules that's being injected. So in addition to using what we know from general chemistry, we can also propose a formula for by using information strictly from mass spectrometry. One of those rules is the nitrogen rule. If the compound has an odd number of nitrogens, then the mass number will be odd. So 86 is even. We should have an even number of nitrogens if there are nitrogens. Right? There may not be nitrogens, right? Like this molecule. There are no nitrogens, right? And we can be told that up front by the percent by mass composition, right? So the no nitrogens, then the nitrogen rule, we don't have to use it. But if we do have nitrogens in the formula, I mean, if we're told there are nitrogens there, then this rule holds. Odd number of nitrogens means an odd molecular mass. Even number of nitrogens, even molecular mass. Okay, fragmentation pathways. If you look on the left, you see the hexane molecule that it has a single charge. It's a single positive charge because we only knocked off one electron. Right? Knocking off one electron leaves an unpaired electron there. And that unpaired electron means that this is a radical. Sometimes we call them free radicals. It is positive charge. That's going to produce the 86, the mass, the MZ 86 peak. But it's possible to knock off, to split bonds, and all these bonds are similar. They're all sigma bonds. So we could break off a methyl group, right? So what would stay behind? Well, the positive charge would stay behind, and the free radical would go with the methyl. So we'd have a methyl free radical, which does not have a charge. How do we know that? Well, let's look at this one, CH3, like that. Okay, what's the H, and there? So what's the formal charge on carbon? Well, that's 4 minus 1, 2, 3, 4, or 0. Has a 0 formal charge. So the positive charge stays behind on the 5 carbon fragment. We could break the bond between number 2 and 3 carbon, and we get an ethyl free radical. Or we could break it between symmetrically, and we would get then one of those fragments would be positively charged and the other one would be neutral. And remember, the only thing that can be detected through our spectrometer has to be charged. Otherwise, it will not respond to the magnetic field. So say with that magnetic sector spectrometer, if you had an uncharged fragment going through the magnetic sector, what would happen? It would fly straight through and hit the wall on the other side. That's it. It would not go to the detector at all. Okay, so there are 3 possible fragments here at 71, 57, and 43. So let's go back. 71, 57, and 43. There's 71. There's 57, which is the base peak, and there's 43. Okay, now, why do we get all these other smaller fragments? That's my question. If we only break carbon bonds, that's what we get. But we can break hydrogen bonds too, can we? Carbon-hydrogen bonds. So that should explain the other peaks, because we got lots of hydrogens in there. All right. Example problem. What is this molecule? This is ethylbenzene. Yeah, ethylbenzene. All right. So the base peak is at, looks like 91 or 92. And the molecular peak is at 10, 20, 30. Each one of those marks is 5. So 105, 106. Looks like 106 is the mass peak. 106. So if we have this molecule like that, we have what? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. How many hydrogens do we have? Well, we have 1, 2, 3, 4, 5. And then this one has 6, 7, 8, 9, 10. We have 10 hydrogens. Okay. So 8 times 12, 12.01. 8 times that is 9608. And then 10 hydrogens is 1.01 is 10.10. At 8, 1, 6, 106. There it is. Okay, that confirms it. Okay, so we're being asked to identify the M plus peak. We did that at 106. What's the formula for the ion responsible for the base peak? The base peak is at what? 90, let's see. Looks like 91. Yeah, they're saying 91. So if it's at 91, it looks like if we break this one off, that's a methyl group. That's a CH3, which is 12.01 and 3.03, which is 4051. We subtract 1504 from the base peak, and that gives us the fragment that's left over, right? This one is not going to be charged. This is neutral. This is going to be plus right here. So this would be 4, 1, 1, 91.14. Right. So that's the fragment for the base peak. The largest peak, it simply has one methyl group removed from the molecule. Okay. And there it is. Now, I wonder why that's the most abundant peak. Well, if most of the bond breaking occurs here, right, you're not going to have a whole lot left over for the full ion. That's why the molecular peak is small. But if we break this one, and then it's difficult to break the others, right? It becomes more difficult to break these others to make the fragments, then they will become less and less abundant. So how about 43? What would 43 be? If we broke this one, that would take, let's subtract 15 more. No, you shouldn't do that. Because now we've got a carbon and 2 hydrogens. So that would be only 202 would be 3 and 14. 14.03. So that'd be 1, 1, 4 is 7, and 1 from 8 is there a 77 in there? 71. Okay. Wait a minute, I'm looking at the wrong one. Sorry. And the rest are minor fragments. Okay. I think I'm tired of beating that horse. Let's move to this one. Now we're going to take a closer look at the spectrum. And now that we know what the molecular peak is, we know what where the base peak is, there's one peak, and sometimes there are more than one peak, but at this point, we're only going to talk about the one peak that's just to the right of the molecular peak, and it's very small. And it's called the M+1 peak. The M+1 peak is, we believe, it's responsible. The responsible party for that one is an isotope of carbon, the carbon-13 atom, which is stable. Right? Carbon-12 and carbon-13 are stable. They're not radioactive. So, and the difference in mass there is just one neutron. So that would add one to the molecular mass. So that's why we call it the M+1. And when we see that peak, one unit to the right, we attribute that to the carbon-13. And it's going to have a value of 86 instead of, I say 87 instead of 86. Now, we see that with carbon because of the relative abundance of carbon-13. It's a little over 1% of naturally occurring carbon. So we're going to incorporate 1% of the carbon atoms in a molecule. Statistically speaking, they're going to be carbon-13s. So we're always going to get that M+1 peak with carbon-based compounds. Whereas the most abundant hydrogen isotope is deuterium. It's only 0.015%, so it's not going to show up. And lesser ones, nitrogen, it's possible that we could see nitrogen N15, but it's only a third abundance of carbon, and it doesn't show up that often. It's difficult to find it. Oxygen, the most abundant isotope of oxygen is 16. 17 and 18 are less abundant, and we can say similar things for sulfur and silicon. I guess silicon could be part of an organic molecule, more likely to have sulfur. Okay, so sulfur could also be introduced because the relative abundance of sulfur 34 is 4%. But the ones that we're going to see a lot more of are the chlorine and the bromine, because they have almost equal abundance of two isotopes of each one. Chlorine will have, chlorine 37 is about 24%, and bromine is about 50% of its other isotope. Now, notice the difference there. Chlorine 35, chlorine 37, that's 2 units. So we're looking at an M+2 peak for that one. And bromine is 2 units. We're looking at an M+2 peak for bromine. But look at the difference in the relative abundance, right? For chlorine, 3/4 of the chlorine will be 35 and 1/4 would be 37. So the ratio there is 3 to 1. Whereas bromine, you're going to have equal abundance of the 79 and the 81. That's 1 to 1. So we can differentiate those two M+2 peaks based upon their relative abundance. And that's what we're going to do next. Here's the M+1 peak for whatever. And the reason it's there is because it's only 1 unit difference. That means one neutron. Whereas when we get to the M+2 peaks, we look at the relative abundance. If you have a mass there, and the M+1 peak signifies the carbon isotopes, the M+2 signifies chlorine or bromine. And for the smaller value, relative abundance, a 3 to 1 ratio of M plus M+2 says it's chlorine because of the relative abundance. If it's a 1 to 1 peak, M to M+2, Then we're talking about bromine. So these are clues that tell you something about the molecule, what's in the molecule. Okay, so here we have bromobenzene. So we should see an N+2 peak that has 2 units greater than the molecular mass. Molecular mass for bromobenzene is 156. We augment that with a relative abundance of equal amounts of the bromine, bromine with 2 extra neutrons, and then we get another peak that's virtually 1-to-1. And we can also see that happening where we have fragmentation. Right? The N+2 peak that we've been talking about is based upon the molecular ion. But the fragments, if they contain bromine in them, they're going to produce double peaks also. And that's the whole point of this slide. All right. So let's see. We have this particular mass spectrum where we can identify, does the compound produce a spectrum shown here, chlorine or bromine? Well, we can find the base peak is 112. We find the molecular peak is at 114. Yeah, the molecular peak is 114. So the M+1 peak, let's see, we got 113, 114, 115. Um, 112 to 114 is an M+2. So let me go back. So are we saying that 112 is not only the base peak, but it's the molecular peak? 112 to 114 is about 3-to-1. So that gives us a, okay. 112 to 114 is M+2, and the ratio tells us it's chlorine. And then we look at 113, which would be the M+1 peak. And then we look at the 115, which is the M+1 based upon the M+2. Okay, M+3 peak. And the relative abundance there is also 3-to-1. Okay, is that making any sense? If we compare the 112 to 114, that tells us we have chlorine. But the M+1 peak also has a secondary peak. That's a 3-to-1 ratio. The 113 to 115. That confirms that we have chlorine in there, not bromine. Okay, let me see if that's what the author is trying to say. Yeah, relative abundance, 33%. Yeah, if the compound were had bromine in it, we'd expect a 1-to-1 ratio, and we don't see it. So it's got to be chlorine. How about estimating the number of carbons from the M+1 peak? We do this by noting the relative abundance of the two. And the relative abundance in nature is 1.1%. So we use that factor as a conversion factor for the value of the M+1 peak relative to the M peak. So that's what we're going to do in the next one. So if you find an M+1 peak, you look at the intensity of the M+1 peak and ratio it to the molecular peak, and then you multiply that times the ratio of 100% to 1.1%, which is the ratio of carbon-13 to carbon-12. That's why that's arranged that way. And if we do that, for example, with this mass spectrum, we find our molar peak and our M+1 peak. The M+1 peak occurs at 5, 10, 15, be 95. So 94 is 100%. And let's see, it's kind of hard to read, isn't it? It's not 10% and it's not 5%. It's like 7. It's about 7% is the relative abundance of the M+1 peak. Somebody dropped something? Oh, okay. Oh, all right. So there's your 7%. So the ratio is 7 to 100, which happens to be the base peak also. And then we ratio that, multiply that times 100 divided by 1.1. And that tells us that we're expecting 6 carbons. We round off to the nearest one. In fact, I think we round down. Well, in this case, it's obvious. We round down to 6. We're expecting to have 6 carbons in this molecule, right? So while we're here, if the molecular peak is 94, and then we have, say, 6 times 12, we're rounding off. 6 times 12 is 72. So 72 of them are carbons. 72 AMUs of carbon. So that means we have 22 AMUs left over for something else, right? So we fill in with, if we had that many hydrogens, we would need, 22 hydrogens, wouldn't we? For this molecule. If we had 6 carbons, and 22 hydrogens, could we make a molecule out of that? No, the most you can get out of that is a linear structure, and that would be 14, right? 14. So we have 7 atomic mass units left over for something else. So it'll either be nitrogen or oxygen or something else. Let's see, 7 would be, what would 7 be? Yeah, 1 nitrogen. No, 1 nitrogen is 14. 4, I don't know. Unless we don't have that many hydrogens. Oh, we can't have that many hydrogens because 14 takes up all the bonds. So we'd have to reduce that further. Yeah. So one feeds on the other. And that wasn't the question anyway. So I'm chasing rabbits now. So here we have strategies for determining the molecular formula from a mass spectrum. Assign the mass peak. Right? At the high mass end of the spectrum, look for 2 major peaks separated by 2 units in their values. If they're separated by 2 units, then we know we've got chlorine or bromine. If there are no M+2s, then M+1s tells us that there are no chlorines or bromines in there. Record the number of carbons. So then we calculate the relative abundance of the M peak and the M+1 peak and use our formula to calculate the number of carbons. Okay. Then we determine if the molecule contains any heteroatoms. In other words, what the mass, is it even or odd? Well, in this case, it was even. So it's possible we have an even number of nitrogens. So 1 nitrogen here would not work if you had 2 nitrogens. Let's see. I'm barking up the wrong tree again. Determine if we have heteroatoms. Does the nitrogen rule suggest the presence of any nitrogen atoms? if an M+2 peak is present, do the relative intensities of M and M+2 and find out if it's bromine or chlorine. And then we can start building our molecular formula with just the relative number of carbons and the presence of bromine or chlorine. And potentially nitrogen. If we see the potential for nitrogen, then we can put a nitrogen in the formula, and we're sort of building it up. Say we would have something like this, that, and maybe we found the presence of bromine, and maybe the rule says there might be nitrogen there, right? But we don't know how many. We know a number here, some number there. We're not sure about that one yet. So we start building up a picture of what it should look like. Subtract the mass of the carbon-12 atoms you determined and the masses of the hetero atoms you determined in the step 3 from the molecular mass. Now, that's a tall order because we don't know exactly. We could say there may be one, there may be three, right? Odd versus even nitrogens. And then you determine, can the hydrogens, if we have the rest of the hydrogens in this molecule, can they account for the remainder of the mass that's left over? If the number of hydrogens is unreasonably high, then consider adding another non-hydrogen atom, like maybe an additional carbon. And the clue to adding another carbon is if you have a value that you've determined had to be rounded. If you round down from, say, 6.5 to 6, then maybe you've got another carbon in there. And you could use that, or you could use an oxygen or a fluorine. All right, so let's take this example. We're not given the M peak, but notice that the two highest mass peaks are 129 and 130. So the 129 is probably the mass, and the 130 is probably the M+1. So we assign that one as the mass peak, and the M+1 peak is 130. And then we calculate the relative abundance. So the 129 is 2.4%, and excuse me, the smaller one is 2.4 on the relative abundance, and 30 is for the M peak. And we determined that we probably have about 7. We have 7 carbons. So we would put 7 here. Okay. I don't know about these yet. Let's wait on those. So we have 7 carbons. Be confusing here. Let's stick with that. Let me write it bigger because it might not show up well in the graph, in the video. That gives us the number of carbons. And then we look at the nitrogen rule suggests the molecule has an odd number of nitrogen atoms. And we can skip the part where M+2, right? We don't have any bromine, no chlorines. So we may have a nitrogen in there, and it could be 1, it could be 3, it could be 5. It's an odd number. Okay. The 7 carbons has a mass of 84 units. And overall was what? 129. So overall is 129 atomic mass units. And this gives us 84. So minus 84 equals what's left over is 44 atomic mass units. Okay. Or did I miss that? 120. 129 minus, oh, can't subtract. Y'all just, I can hear you giggling under your breath. What's that? 45. There we go. 45 atomic mass units left over. How about an odd number of nitrogen atoms? Since the nitrogen rule suggests that there are odd numbers, but how many? If we assume the compound contains 3 nitrogens, that's 42, right? And that would take all but 3. And then there'd only be room for 3 hydrogens left over. It's unlikely that we have 7 carbon atoms and 3 nitrogens. That would only leave us 3 hydrogens because of the way that you would have to structure them. Even if we only had 1 hydrogen per carbon, 3 is not enough. So if we, rather than 3, if we go to 1 nitrogen, that would be 14, right? So if we had 1 here, right, that would be minus 14, and that would be 31 atomic mass unit. Okay. The 31 hydrogens is too many. We can't put 31 hydrogens in that molecule. So there must be something else in there. There may be a 7th carbon, right? There could be some other atom like an oxygen or a fluorine. So if we pick up, oh, wait, we've already got 7 carbons. What am I saying? So instead of going with an extra carbon, because what was the ratio before? The number of carbons? 7.3. That's too close to 7 to add another carbon. So let's not try a carbon. Let's try an oxygen or a fluorine. So maybe an oxygen here, or maybe, we don't need that, a fluorine. So if we used an oxygen, that would be what? 16? No, yeah. Wait a minute. Oxygen would be, yeah, 16, right? So if it were oxygen at 16, then we'd have 15 atomic mass units for the hydrogens. Or if it were fluorine, we'd have, let's see, fluorine would be 18, right? 8. And that would be 13 atomic mass units for hydrogens. Okay? Did I do that right? This one looks right. Do my fluorine. Oh, it's 19. Excuse me. 19. That's the most abundant isotope of fluorine is 19. So this would be 12. Okay, now it makes sense. Okay, so if it's oxygen, right? We have 1 nitrogen, 1 oxygen, or 1 nitrogen, 1 fluorine, and this would be 15, and this would be 12. So those are 2 possibilities, the most likely possibilities for this molecule. Okay. If I keep talking, we're going to run out of time. Let's see, how far along have I come? Am I even halfway yet? Roughly. Okay. So, this unknown has a mass spectrum shown here. Propose a molecular formula for the compound. All right, so we're identifying. We've got these peaks at the far end are 150, 151, 152, and 153. So since we have a peak at 152 that's 2 units away and about the same height as 150, we assign, let me erase this. We assign 150 as the mass peak. Right, so 150 is the M peak. 152 atomic mass units, and this is equal abundance. That means this one is bromine. Okay. And each one of those, and then we have a 151, right? A 151 atomic mass unit. We need the relative abundance of 151, which is 0.7% versus 14.7. So 0.7 versus 14.7, was it? Yeah. And this is times 100 over 1.1. And that will give us the relative number. It'll give us an estimate of the number of carbons. Excuse me. All right. So that says that this is 4.3 carbons, or 4 carbons. When we start to build up a picture, C4 is where we're starting. Then we know there's a bromine in there. We don't know how many hydrogens there are yet. And then if we say with 4 carbons, that's 48 from 150. So 150 minus 48 carbons would give us 62 left over. No, I subtracted it wrong. 48. Oh, minus 79. 79 is for bromine. Okay, so we're gonna have take away the bromine, and that doesn't work, does it? 150 minus 48 minus 79. Well, it should work. I got the wrong number here. That's the problem. This is 2, and 4 from 11 is no. Oh, 10. There we go. Minus 79 then gives us 23. 23 atomic mass units unaccounted for. So can we account for that with the number of hydrogens? Not too many hydrogens. Right. 23 hydrogens would be too much. So since our value here was 4.3, it's probably not a carbon. So it could be an oxygen or it could be a fluorine. So if we say C4H, oxygen or fluorine. So with 23 left, minus 16 would be 7. So this could be 7, or 23 minus 19 could be 4, right? Oh, it could be. So those are 2 possibilities. C4H7BRO or C4H4BRF are 2 possibilities for this molecule. Does this make any sense? It's a treasure hunt. Trying to use these rules that help us simplify interpretation of the mass spectrum. Okay. So what other information can we gain from this spectrum? If we follow the fragmentation pathways for chemical processes, maybe we can identify other ions that are in the spectrum that we haven't approached yet. You know, the lesser mass structures. Are they going to tell us anything that we need to know to help build a molecule? So far, we've only approached this in terms of the molecular formula, right? We haven't talked anything about structure yet. Okay. So for alkanes, the base peak, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The base peak is going to be that first ionization. No, excuse me, the molecular peak is going to be 86. Loss of 1 electron. Okay. So where could the breaks occur? Well, we could get a break with a methyl group, and that would give us a pentyl radical with the methyl left behind, right? That would only be 15. So if we go back to there, all right, there's the 15 peak right there on the left. Right, that's the methyl radical. If we broke it at the second part, then we get an ethyl radical, and that would be well, all right. Here's what the author's trying to tell us. Where is the charge going to go? If we had an ethyl radical, what would that be in terms of mass? That would be 2 times 12.01. Let me make some room there. Let's take a second. Distraction out of the way. 2 times 12, let's just round it off. So that's 24 for the carbon. And how many hydrogens? 5 for an ethyl radical. Yeah, 5 carbons, which would be 5 here. That'd be 29. Is there a peak for 29? Yes, there is, right? So one thing that can happen is if you break between the second and the third carbon, the positive charge could go either with the ethyl group or with the butyl group. If it goes with the butyl group, then you're going to have a 57 as your mass. And there's a peak for 57. Yep. That's the base peak, as a matter of fact. Okay, so we've accounted for 15, 29, and 57 with just those breaks. What if, are we likely to get a pentyl cation? Right? If the what's the base is 86, with 86 as the molecular group, and if we subtract 15, move on to 71. So do we get a pentyl cation? Let's go back and look at 71. Yep, there's a 71 there. So that is also a possible fragmentation pattern. So when you break that bond, you could get the radical to go one direction and the cation to go the other direction, or vice versa. So out of these 2 breaks, we could get 4 peaks. All right. Now, if we look at the size of the peak, we're also looking at which one is the more stable cation. All right, so let's go back. All right. If we break here with the ethyl group, which one would possibly have a more stable cation? Well, the butyl would be the more stable cation. Right? Even though we put it on the end, we could have a hydride shift and move that plus charge over to a secondary carbon. That's a more stable. So the more abundant one out of the 2, butyl versus ethyl, is going to be the butyl. So the ethyl was, which one? Ethyl was 29. Right, this is the ethyl. And 57 is the butyl. More stable is this one. So it should be the larger peak. 57 versus, where is it? Wait a minute. Oh, here we go. 57 is a massive peak. That's the butyl peak. It's the more stable carbocation. Whereas 29 is a smaller peak here. Okay. And the secondary carbocation in this case. Now, if we're looking at 2-methylpentane, what's the more stable carbocation? It's going to be the tertiary carbon. So instead of breaking between 2 and 3 carbon, if we break between 3 and 4 carbon, that's going to give us a tertiary butyl carbocation, which would be much more stable. But I don't see that one. There's a 43 they're saying is the more abundant. Why is that? Well, probably because the bond between that number 2 and number 3 carbon is weaker, of the weaker one of all the other bonds. Okay, that's the point. It doesn't say that, but I think that's why. Yeah. Otherwise, if it broke between the third and fourth carbon, then we would end up with a tertiary carbocation, which is much more stable. But the bond between the third and fourth must be stronger than the one between 2 and 3. That's the only thing that makes sense to me. All right, how about 2,2-dimethylbutane? All right, 2,2-dimethylbutane. Weren't we we're looking at that one? No, this is a new molecule. With additional branching, fragmentation gives rise to fragment ions with relatively high stabilities. If a fragment ion is sufficiently stable, then the M+ peak can essentially disappear entirely from a compound's mass spectrum. Okay. Oh, okay. So we could mistake this peak at 72 for the molecular peak when it's not really the molecular peak. Ooh, that could be a fly in the ointment there. All right, so we have to be careful of that one. You know what? If you're going to use mass spectrometry, I think before you even go into this, you need general chemistry outcomes for molecular formula. That's what I'm thinking. Right? You don't even want to go here until you have a molecular formula, right? And you can get that easily with percent composition and molar mass. Okay, once you've got that, then this would be a helpful tool to go beyond. Yep. Okay. So how about alkenes and aromatics? How do they fragment? Loss of an electron from the pi bond gives you a pretty substantial peak for the molecular peak. Because all we have to do is knock an electron off, and now we've got an ion, carbocation. Okay. Did we lose anything else? Nope. We just lost an electron and converted a double bond to a single bond, right? So that should be fairly reliable as a molecular peak at what, 80? Let's see, 84. Yep, 84. And not only that, but if we then break a bond, say we break off a ethyl group, and the more stable carbocation is going to be left on the butynyl cation. What happens with that extra electron is it pairs up with the radical electron and makes a double bond. And then we can resonate between those two butenes, butyl cation. Okay, so that should give us a substantial peak also at 55. Is it? Oh yeah, that's the base peak. That's extremely stable. So relative abundance is accounted for by the stability of that resonance structure. How about benzene or a substituted benzene? We have 1, 2, 3, 4. We have a butyl substituted benzene. Okay, so we're saying that the molecular peak is at 134. Okay, I'll take their word for it. But we got a base peak at 91. How did we get 91 out of that? Okay. If we break off a propyl group, propyl radical, that leaves us with a very stable benzyl cation. Yep. Now, why are we rearranging to give us a tropylium ion? That's 1, 2, 3, 4, 5, 6, 7. That's 7-membered ring. That gives us a, well, both of them do. Both of them, well, okay. The that primary carbocation is not very stable, right? It would resonate with the ring structure, and then to stabilize it further, we would rearrange. Yeah, we would rearrange the ring structure. Now, is that going to be aromatic? That tropylium ion? 2, 4, 6. Okay, that's an odd number, assuming it's planar. How about that carbocation? Does that have a p orbital available? 1, 2, 3. Yes, it does. Okay, so this should be an aromatic molecule, that tropylium ion, which means very stable. Okay. How about, what do we do about alkyl halides, amines, ethers, and alcohols? What do they do to the, well, they all have hetero atoms in them. And hetero means other than what? Other than carbon or hydrogen. Right? Many functional groups contain these hetero atoms and can play a role in the fragmentation pathway. They can determine where the breaks occur. And one of the most important features of these heteroatoms is that they often have non-bonding lone pair electrons. Especially nitrogen and oxygen definitely do. Sulfur does. They have non-bonding lone pairs. And these are the least tightly bound electrons in the molecule, which means that they can easily be knocked off with that electron storm that comes from within the pathway that the molecule has to traverse. So in the ionization of the molecule, a lone pair is generally the most likely electron loss to produce the, okay. So here we have chlorine. So now we're going to have a positive charge on the electron. And what does it do? Well, the chlorine leaves. Right? The chlorine is positively charged. It wants an octet. So it takes one from the bond and it leaves behind a positively charged species where the carbon is actually neutral. Okay. This is heterolysis. Both of the electrons from that carbon-chlorine bond go to the chlorine. Yep. And leave behind 1, 2, 3, 4, 5 carbon tertiary carbocation, which is very stable. Yep. which means that the molecular peak will not appear. Why? Because the molecular peak must have chlorine in it. And the carbocation is so stable that chlorine is going to leave. So we have no molecular peak out of this one, simply because of the way that chlorine is it leaves the group. That could be a problem, because now we don't have any way to determine the M+2 peak and confirm that chlorine is there, at least not by the mass spectrum. We would have to confirm that by the molecular formula, determined independently. Okay. All right. Alpha cleavage is the elimination of an alkyl group from a carbon atom bonded to the heteroatom. So this is another possibility for that molecule. Rather than lose the chlorine, we lose the methyl group. And if we do that, then the positive charge stays behind, and we get a mass peak of 91. Let's go back. Is that the same molecule? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, it's the same molecule. It's being, we're getting a bond cleavage at a point that leaves us with 91. Okay, 91 molar mass. Excuse me. Another alpha cleavage could happen on the other side. So there are two, we could have an alpha cleavage on the right-hand side, and either one of those methyl groups could leave. But if we cleave on the other side of the carbon, then an ethyl group is going to leave. And that'll leave us a mass of 77 rather than 91 for the other two. So this alpha cleavage is common because the chlorine has an electron withdrawing effect from that carbon, and it weakens the bond between the alpha carbon and its neighbors. So we have actually only two possible breakages there on that alpha carbon. Okay, alpha cleavage in amines. Does that work? Okay, the alpha carbon is connected to the nitrogen, and then what other cleavages can occur? Well, there's only one. In this molecule, there are three methyl groups, and they're all identical. Right? So as far as our mass spectrum goes, any one of those could break and leave behind that, it's called an iminium ion. An imine has two carbon-based groups on one side and a double bonded to a carbon on the other side. That's an imine. And in this case, that gives us a huge peak because it's very stable. Stability, in general, determines the base peak. How about ethers? Where's an ether going to cleave? Doesn't say. Why doesn't it tell us? Oh, fragment ion from alpha cleavage equals 87. So the alpha cleavage would just be losing one methyl group. Right? It has two alpha carbons, one on either side. So, and they all have the same methyl group. So you lose one methyl group. That's it. But that's more stable than the molecular peak. So the molecular peak is very, very, very small. You can just barely see it down there. So is that actually true? If the molar mass is 102, and we did a methyl before, right? 12 and 3 is 15. So that's 7 and 1 from 9 is 8. 87? Yeah, okay, so that's right. We chopped off one methyl group And that leaves us with that alpha cleavage peak at 87. Now, notice that little peak to the right of 87. I'm thinking that's an M+1 peak, or an alpha cleavage +1 peak. Okay, how about this one? A primary alcohol. So what's going to happen here? Let's see. Is it going to tell us? Other cleavage in alcohols. All right. Well, we could cleave a carbon hydrogen bond that leaves 88. 1, 2, 3, 4, 5. So this is pentanol. 1, 2, 3, 4, 5. Yeah, that's the same molecule. Pentanol, if we chop off a hydrogen, that's just going to reduce the mass by 1 atomic mass unit, right? So instead of 88, it's going to be 87. Oh, that's what they're saying. M minus a hydrogen gives us 87. M minus a water, right? If we chop off the hydroxyl, is that going to work? Loss of a water. Okay, if we chop off a hydroxyl, it needs a hydrogen from somewhere. Right? So it's going to take a hydrogen that leaves the carbon that's most stable. So in this case, what we typically see is when that cleavage occurs and we remove the hydroxyl, it's a strong base. It's looking for a hydrogen, and the gamma hydrogen is probably the bond between that carbon and the hydrogen is the weakest. So that's why we remove a water when that happens, because the hydroxyl can't stand alone in that environment. It's going to accept the hydrogen that comes off of that same molecule. So what we're seeing is a double cleavage, right? We're seeing a heterolysis of the hydroxyl and then a homolysis for the hydrogen carbon at the gamma position. Okay. How about carbonyl containing compounds? We typically lose a lone pair electrons from the carbonyl oxygen. Well, actually, we only lose one electron because we want one positive charge. Okay, so the loss is loss of a non-bonding electron. Okay, and then we get an alpha cleavage. The acylium ion apparently is very, very stable, right? That's odd. That I've never seen that one before. Well, I guess I have because I taught the course before, but I haven't seen it in a while. Okay, so that's where the 43 comes from. It must be an extremely stable oxocation. That's what I'm going to call it. Let's see. Oxygen starts off with 6 valence electrons, and that's 1, 2, 3, 4, 5. 6 minus 5 is 1. Okay, that's a +1 charge. Okay. So that's what you can expect from a carbonyl. McLafferty rearrangement. So why would we get a McLafferty rearrangement? The carbonyl containing compound undergoes a cyclic movement of 6 electrons to produce an enol radical cation and an alkene. All right. Well, we only have 3 arrows in there, so that's kosher. I don't see how that works. We eventually break. Oh, they're showing us how the alpha breakage occurs, right? And that produces a neutral alkene plus an enol radical. And the enol radical in this case is going to be 58. And 60? Why does it say 60 when it's left a 58 behind? That must be a typo. Do I see a 58 in there? No, I see a 59. I don't see a 58. What if it loses? What if this also loses a water? Right, that'll be 18 minus that, which should be 60. Yeah, there's a 60 peak. Okay, that's what happened. It left that detail out. So what's going to happen is that mass of 60 is, we take the enol radical, which is very unstable, and water, the hydroxyl is going to leave, and it's going to pick off an alpha hydrogen. And that reduces the mass by 18, which is the mass of water, right? So 58 minus 18 is 60. And that's why you get the 60 peak. All right. Is that enough for one day? That's enough for 2 days. That's enough for a whole weekend.